Okay, and so she's going to give you a lecture on wireless local area networks. Now, this lecture is very relevant to your lab work, so it's very important that you try and understand as much as possible about wireless local area networks. Okay, so I'll leave you with Zainab.
Thank you, Zaidi. Okay, good afternoon. Everybody can hear me at the back? Can you hear me? Okay. If my voice doesn't reach you, please let me know. Or if you have any question, please also let me know. I think I used almost similar slides.
Every speaker is not on.
Really? Thank you. Okay, so what we will do today, basically 802.11 is the most popular standard for wireless LANs, although we will also touch upon HyperLAN. HyperLAN is the European equivalent of 802.11, but the focus of the presentation will be on specific .11 technology. B and A, actually 11B is the standard which is initially deployed in the devices. So, in detail we will go over 11B and then look at the differences from B and A. Just I have this slide for wireless lectures. It just looks good. We have clutter of wires. Why we want to have wireless LANs? Because to have a clear workspace, have flexibility of moving wherever we want. This picture is actually not the right one because we are talking about wireless LANs, which are basically indoor networks. But here, the mobility concept is extended to wherever you want to work. If you want to work on the beach, yes, you have satellites and cellular stations there. But anyways, besides having ease of operation, the other important thing is it provides its robustness. I mean, think about a situation when you have earthquake or part of the building is damaged. In case of wired networks, it might be possible that some of your critical nodes are within that damaged structure, and then you have to relay all of your network. In case of wireless, it's most possible that some of the nodes are gone. Okay, rest of the network is working. And network planning is not really important. We don't have to lay wires from one room to another. And you just have to, hook up your devices wherever you want. Although, you still have to do some planning. But that was something, if I want to sell a product, these things really sounds good. But as far as engineers are concerned, people who were thinking about writing the standard 10, 15 years, 20 years ago, these are the challenges they faced. Yes, it's all good that we have wireless network, but it has some cost. And what is the cost? Radio propagation is inconsistent. Wireless medium is dynamic. It changes all the time. Then we have noise interference, because if you are working in open license, because if we want to really cut the cost down, we really have to focus our technology in the open license spectrum where we don't have to pay for license fee. But everybody can use the open license spectrum. So there will be, if there is no interference right now, I mean, I'm talking about if we are thinking in terms of the engineers who were sitting and writing the standards 20 years ago, even if there was no interference at that time, they could envision that there will be a lot of interference in future. And then multipath reflections means that if I send an electromagnetic wave, a radio wave, there will be a line of sight component, but there will be other components which will be reflected from walls, obstacles, and those obstacles might be moving. So So it's very interesting. Even in indoor environment where we have access point and people who are using laptops are accessing that access point and everything is stationary, but just because people are moving within the room, multipath environment is changing. It's very similar to having a mobile node accessing the network. And then we have fading. And fading is something which is very difficult to model. Although there is fading because of the distance. If the node is very far from the access point, yes, the signal will be weaker. But it could happen that your node is quite closer, but there is an obstacle which is obstructing the line of sight component, and signal becomes very weak. So, there might be different things which affect the radio signal. And similarly, if people are moving or if the distance between the access point and the node is changing, there is this Doppler component over there, which means the frequency of your signal is also changing. Security point of view, open medium, people can eavesdrop. Smart eavesdroppers who have transmitters, who have receivers, they can tune into your frequency band and listen to whatever your conversation is. Interference to other devices. Hospitals now increasingly use wireless devices in critical situations. Even our mobile phones can interfere with that. And we all have this problem when we are traveling. We have to switch off our mobile phones, although mobile phones are using different frequencies than the frequency used by the controllers and the aircraft. But still, our mobile phones can interfere, right? It can be noise to that communication. So, interference and radio medium issues are there. Another thing is even spectrum is called open, but it's limited. So it's not that we can have as many users as we want and we can use frequencies as much as we want. It's a limited spectrum. So it needs to be used efficiently. Another thing is people who are developing devices, it's very important for them not to just target one country. They want to have some devices which could be used in other countries so that they can have extendable market. And in this case, especially 20 years ago, different countries have different allocations for open license. So most of the problems were gradually overcome, but still, interestingly, in US and also in Europe, 900 megahertz, a piece of 900 megahertz is also free of cost. It's also open. And there are devices in US where you can have a wireless LAN operating in 900 megahertz. In NICTA, we also tried to use those devices here, and then we realized, actually we knew that part of that open spectrum is not available in Australia because, a chunk of that spectrum is used for GSM. Oh, not GSM, it's 3G, basically cellular phones. And, these devices, although they pass all the quality checks and yes, it's FCC approved, it's SCMA approved, all the committees who are taking care that people are using what is specified, but still it's not that accurate. Accurate, I guess, is the right word. So when we use those cards here, what happened that our signal leaked into the 3G spectrum, cellular spectrum space. And in one of our experiments, and we didn't know it until later, we got a call from ACMA that we were jamming some of the cellular calls. So these issues happen just because there is no single standard worldwide. People have different allocations in different countries per spectrum. Following on from the last slide, in terms of technical issues, it's very important to use the spectrum efficiently because users we have right now will increase. They won't go down. And even now in 11B space, we have even I don't have a device right now, but it's very interesting, which actually shows you the utilization of different frequency bands, and it will show you that if I don't have it right here, but we tried it in NICTA, and it shows that almost at one point we had more than 80 access points accessing the same frequency band. And it is not unusual. I mean, if you look up in your laptops how many active access points are there, usually there are more than 10, right? And usually in universities, they will be easily more than 50. So it's very important. We need capacity. We will have more users in the future, and we need to provide them all with a good quality of service. Security is a problem. We will see how these things are mitigated. Power efficiency is important if we have battery operated devices. So far in 11B, or actually in 11A, laptops are used and access points are attached to one point where power from mains is available, so it's not an issue. But if you have PDAs or smaller devices which are battery operated, then using power efficiently is also a big issue. We will see. In a standard, in .11 standard, they also have a power efficiency issue there. Low radiation is also interesting. Every government has a policy in terms of if you have an access point, antenna, and transmitter. The policy says that within the let's say 3 meters, the power should not be over 1 watt. So it's not that if you want to increase the coverage or if you want to reach the other nodes, you can just power up your device. You cannot do that, right? So low radiation is there, and we have to work within those constraints. Ease of operation, these devices are made for common users, people who are not really technologically sound. They just want one push button for the device and everything is set up. So things should not be complicated. And global operation means that governments should come together and decide on similar allocation of frequencies. Cost again, there is no point that for wireless LANs we go for licensed spectrum. It's just not cost effective. And here are some questions. We have to keep in mind that we are thinking in terms of those engineers who were sitting 15, 20 years ago and thinking about writing a standard for wireless LANs. Infrared is also wireless, right? And even our older computers all have infrared interfaces. Why not infrared? No license, low cost, already available on the devices. So what do you think? Why not? It's line of sight, right? Line of sight and very low data rate. So, correct. And another thing is, even 15, 20 years ago, we had cellular available, GSM. So why not? Wireless, fully mobility supported, and available, basically. Why not? Why didn't people think about that? Or even now we have cellular phones, and we have now the data features available from cellular phones. But why not? It's very expensive. Even if we use 3G modems, it's still very expensive than the wireless LANs we have here, and we can have a cheaper solution for the indoor connectivity problem. We don't really need a big, expensive network. So it's actually the paper I cited here was 2003, and so many modifications have happened since then in cellular technology. It's going towards more and more broadband and data. So the data rates reported here, 20 to 50 kilobits per second, is now changed. It's not that small, but still the service versus cost trade-off is still in the favor of wireless LANs rather than cellular systems. Any questions so far? Anything? Okay. So that starts our .11. Is there any confusion at the back at the last row? Everything is okay? Okay. .11 is basically, when it's proposed, what we call Wi-Fi is basically 802.11b standard. And A and B and G, and there are many alphabets there. 11b and 11a came at the same time, 99, and they differ in lots of things, and we will see that. But the major difference is the frequency band they are using. 2.4 gigahertz is 11b frequency band, and 5.1 till 5.8 is the frequency band for 11a. Interestingly, the manufacturers are more interested in using 11b because if we have studied in electromagnetic physics that if you have higher frequency, the coverage is smaller because wavelength is smaller and you cannot reach far. So 11b in terms of coverage is better than 11a, and manufacturers were more interested in coming up with a cheaper device quickly. So what we call commonly as Wi-Fi is basically 11b. Interestingly, here I have some numbers, and it shows that outdoor range is approximately 100 meters and indoor range is approximately 30 meters. Why do you think there is a change, there's a difference in indoor and outdoor range? Why indoor range is smaller? It's because of the walls. Even if we have larger halls, but they have walls because signals are reflected, and multipass can degrade your signal and also enhance your signal. It depends on how they are coming together. So in general, indoor performance of signal propagation is worse than outdoor because in outdoor signal get free space. So indoor range in general is smaller than outdoor. Another difference in the number is here, where we have data rates as 11 megabits per second for 11b, and then there is a column for throughput, which is 4 megabits per second. So data rate, throughput. What do you think? Why this difference?
Overheads.
Overheads, exactly. There is one thing which is overheads. Data rate means just the raw data rate, bits going into the medium. So you have headers, you have checksums. Another thing is data rate is how much data you can put it on the medium. But if I am using one node as a source and one node as a destination, source is sending to destination, destination is sending acknowledgements back to the source. So it's a two-way communication, and data rate just tells you what you can put on the medium. It doesn't care about two-way or one-way. So basically the data rates are divided by half automatically, and then on top of it you have overheads. Okay. Some nomenclatures. Infrastructure network term is used when we have access points which are connected to the wired networks, and the last mile, the last hop of the network is wireless only. Most of the wireless LANs are infrastructure type. And they are wireless just because the last hop is wireless, otherwise the whole network is wired. The devices can also be used in ad hoc mode, peer-to-peer. They can also talk to each other. But in most of the devices which are available commercially, ad hoc mode is there, but it's not really supported. So you can put your devices in ad hoc mode, but if it doesn't work, nobody takes the guarantees. But infrastructure network is something where people are really putting the focus, and it has really matured over the years. Another thing, some terminologies. We will use these terminologies later. If one access point connected with different stations is called a basic service set. So if we have an access point here in this room and your laptops are connected to that access point, they will make one basic service set. And if the access points are connected to one network, all base stations can make up an extended service set. Like there will be an extended service set for UTS, or maybe an extended service set for building 10. And the network basically is connected to the 802.x LAN, means the Ethernet, the wired traditional kind of network. What we say as .11 standard is nothing but defining what will be the physical layer and what will be the MAC layer in your OSI layers. So all of the 7 layers, wireless LAN doesn't care what you have in the logical link layer, or IP is basically used, TCP IP, and what do you have in the application layer. They basically are the same. So whatever we were using in Ethernet, all the things as in a similar way are transported to wireless LANs. The only thing which has changed is MAC and PHY. So PHY means, you'll see actually in the next slide, PHY basically means what modulations we are using. PMD, actually PHY layer is divided into 2 sub-layers, where one layer talks about what modulation, what coding, and how to use the physical medium. Whereas this PLCP, physical layer convergence protocol, wherever you see this word convergence, it basically means that it is acting as an interface between the lower layer and the upper layer, right? So this PLCP is acting as an interface between the PHY and the MAC. MAC needs to know if there are multiple stations interested in accessing the medium, when a station can access it. And it needs information from PHY. Okay, medium is free or not. And this information is supplied by PLCP. And MAC, as the name suggests, medium access control, it basically has algorithms and protocols where multiple stations can access the medium in a certain way. Let's go back to the previous slide. And here I have, this is the protocol stack for mobile terminal. This is the protocol stack for access point. So access point has dual interfaces because it's connected to the wired network. So it has this .3 is the Ethernet standard. So it has Ethernet MAC and PHY as on one interface, and has .11 interface to connect with the mobile terminals. In this slide, we also have these management layers. So there are some technical issues which are solved in here. How do the devices access the medium? What modulation is used? What coding is used? But on the same side, we also have management issues. For example, when you try to access a network, you need to, when you click on it, it does some negotiation. Association is done. So some information is exchanged. If you are an authentic user, or if you are a legal user to use that network, the access is granted. So all those management issues are basically, all those protocols are in those layers, MAC and PHY, management layers. Any question here? Everything is crystal clear? No? There's nothing actually. In between, okay. But if you have any questions, please stop me, because it's better if we have an interactive lecture. It will be much more easier to understand it. Otherwise, I will just speak. What actually I'm doing now is, let me go back. This is now our slide, and we will go over each layer, each sub-layer one by one. So starting from the bottom, we have modulation, physical modulation. And here there are three, in the initial standard, .11 standard, 3 phi layers were defined. And we will first study the phi layer, which is not very interesting to the manufacturer, so you won't see it in most of the devices, but we'll still look at it. And we will compare why it was not picked up by the vendors. So 3 versions were defined. First one is frequency hopping spread spectrum. Okay, have you heard about frequency hopping term before? Okay, good. So how things are done? We take one channel, divide it in 1 megahertz slots, and the device actually uses multiple of these carriers and change those carriers after a certain time. I think, yes, it's here. 2.5 frequency hops per second. Like in 2 seconds, each device will make 5 hops. So if a device is using carrier number 2, it might hop on to carrier number 88 within the band which is allocated to the device. And how this hopping is being done is by using a pseudo-random hopping sequence, right? So it's not random, but there's a mathematical way of generating these pseudo-random sequences. And the whole idea is, if I have, let's suppose, 10 devices using the same channel, and I will have pseudo-random sequences for each of them. If my sequence is really large, it has multiple digits, there is very less chance that 2 of the devices will start using the same carrier. Because if they start using the same carrier, there will be a collision and none of the transmission will be received properly. So what we want, that even if they're using the same channel, they will be using a different subcarrier. But another thing is, if we can allocate them statically, the subcarrier, why do we want them to hop around? What do you think? What is the benefit of having hopping? Security is one issue, and basically frequency hopping was devised to counter the security threats. People who are trying to eavesdrop on you, they can tune into your frequency, find out where the transmission is going on. But even if they have tuned into your frequency, after a while you will switch to another one, and they don't know it, right? So till the time they are tuning into your transmission, you will switch. So you will hop to another frequency subcarrier. So security is one issue. Another thing is we also have frequency selective fading. Some of the fading issues are happening on certain frequencies. So it might happen that at a certain time of the day, frequency carriers from 10 to 15 are down. Their characteristics are very poor. So even if a device hop onto some of the carriers between 10 to 15, it will hop away in a while. So some part of the communication will be gone, but not all. But if we statically allocate the subcarriers to a user, all of the transmission will be gone, right? I have another word highlighted by orange color, which is GFSK modulation. So what do I mean by that? We have subcarriers. Subcarriers are allotted to the devices, and the devices have to use this GFSK modulator. GFSK is nothing but Gaussian frequency shift keying. FSK, which is a known modulation scheme. Gaussian frequency shift keying is the scheme where we use FSK, but before doing the before going through the modulation, we do a Gaussian pulse shape. Pulse shapes are basically rectangular. We put it into a pulse shaping filter and change the shape to a bell curve. These rectangles with the sharp edges have poor spectrum performance. You know, they have sidebands which are going into, actually theoretically they have indefinite sidebands. But if you use this bell curve pulse, it has much lower sidebands than rectangular. So if we have Gaussian pulse shape, the pulses will have better spectrum performance, and actually, you know, we can call them narrowband. Narrowband means they are not leaking into outside the band. They are basically within the band that is allocated to them. But FSK is something which is a standard, you know, frequency shift gain. What do you think? What is the frequency shift gain modulation? Brush up the memory. Remember anybody? Huh? You can make a guess. Yes? Exactly. See what we have. We have bits, and bits are 0 and 1. We need to have some way of sending 0 and a different way of sending 1, right? Like in PSK, phase shift gain, we use different phases. Like 0 degrees is for sending 0 bit, and 180 degrees is for sending 1 bit, right? In frequency shift gain, what we do, we define 2 frequency levels, and you know, if they are far from each other, obviously it will be easier to demodulate it. If they are very close to each other, both of the levels, noise may interfere, and it will be very hard to demodulate. Maybe a 0 is sent, and we will receive a 1, right? So in frequency shift gain, what happens, the different levels are defined. In normal frequency shift gain, 2 levels are defined, 1 for 0, 1 for 1. And Gaussian pulse shape, I worked on it. So basically what we have here is this is basically not the modulator, it's a pulse shaper, and then the signal, then the user's data comes into the modulator, where we have a hopping sequence telling the modulator which frequency levels they need to use. So each 1 megahertz will have then 2 frequency levels defined in it. And that signal will be transmitted. It's a modulated signal. Anything which is not clear here? Okay. So doing that and using these 1 megahertz spacing between the subcarriers, the data rate could be up to 1 megabits per second. But in the bracket, we also have 4-level GFSK for 2 megabits per second, which is basically, instead of using 2 levels of frequencies, now we are using 4 levels within 1 megahertz. So now we are packing more bits. And another thing, if you are using 4 levels, what does it mean? How many bits we can use for one small band of 1 megahertz? We have 4 levels. So how many bits? 2, right? 0, 0 is mapped into 1, frequency 0, 1, 1, 0, and 1, 1. So now, in the beginning for GFSK case, we had 1 megahertz, we defined 2 levels, and we were mapping 0 to 1 frequency and 1 to another frequency. Now we are mapping 2 bits to 1 frequency level. Still, we are using 1 megahertz subband. So the consequence of that is our data rates hasn't doubled. We now have 2 megabits per second data rate. The cost is what? What do you think? What is the cost? Because if it's such a good thing, why do we have GFSK then? Just use 4 level, or maybe even more. Use 8 level. What do you think? What is? The complexity will increase, and your demodulation will become erroneous, right? So if the thing, how these things are worked. If your node is very near to your access point, right, and your signal is really good, you can use GFSK. You can use 4-level GFSK, right? Has 2 megabits per second data rate. But if your signal is really, kind of changing all the time and varying and is not really good, better to use GFSK 2-level, right? So, compromise on the data rate, but still have some communication. Because if we still use 4-level GFSK, things are moving, so signals are moving, and it will be very hard for you to differentiate what actually was sent. Because now the difference between the levels is smaller. Data packet format. We have payload. Payload is something which is coming from upper layers. So even this payload might have MAC headers. Phi doesn't care. For Phi, this is payload that it needs to send on the medium. So Phi has synchronization bits. Synchronization are nothing but 0101 pattern, which basically allows the receiver to synchronize their, what they understand, what is the bit timing, where 0 starts, where 1 bit has actually started. They can synchronize their receivers to what is coming on the medium. And the different synchronization bits are used in FHSS. 80 bits are used for synchronization. We will see there are different standards. SFD is a known pattern which tells the receiver that now the frame is starting. Okay, so when the receiver looks at this pattern, it will know that, okay, whatever the rest is coming after that is the actual frame. Here we have length of payload, because there is no fixed length. Payload could be smaller, payload could be larger, depending on what your application requires. And PSF is a signaling field which actually says it's a 1 megabit data or 2 megabit data, because see, we have used 2 different modulation schemes. One has double data rate than another. So receiver should know which demodulation to be used, right? So this signaling field actually tells the receiver that they should use GFSK 2-level or 4-level. And header checksum, because this is important information, we need to have some safeguard for it. Header checksum, how does it work? It basically has this this remainder value, CRC remainder value. You add this remainder to whatever is the remaining header, and if it is divisible by a known polynomial at the receiver side, these CRCs are standard, so receiver will know what polynomials they have to use. If it is completely divisible, it means that the header is error-free. Or if there is, if you still have some remainder, it means that something is wrong. Interesting point. Actually, I have a question here first, which is basically, we have 1 megabit or 2 megabit payload. What about the header? What do you think? Can I still have 1 megabit or 2 megabit payload? Oh, sorry, header. Because all of these bits, when I will have the whole stream, I will send it to the modulator, and they all will be modulated over GFSK. So what do you think? We have talked about 2-level and 4-level GFSK. Should I use both of them for the header? Or, if the signal is good, I can use a 4-level GFSK. Or there are some consequences which I should be worried about. Think about it. Any guess? I mean, or let me put it in another way. If I have multiple modulations defined for the header, will it work okay, or there will be a downside of having this multiple modulation for the header? Any guess? I think you can make a guess. Nothing. No, there is no wrong answer here. So even if you say yes, it will work, it's okay. I will explain to you. So what do you think? Will it work if I use multiple modulations for the header? Yes. Okay. How the receiver will know that which demodulation I need to use? Because here we have a signaling field which actually tells the receiver, now you have to use 4-level or 2-level demodulation for the payload. So if we don't have that, if we don't tell the receiver which demodulation they have to use, they would be in dark, right? So multiple, in all of the .11 standards, multiple data rates are defined in the standard, but only for the payload. For the physical header, one standard, one modulation is used. So I think I will see, I'm not exactly sure, but most of the headers are 1 megabits per second. So they all use 2-level, and if the signal is good, the signaling field will indicate that now for the payload, the receiver should use 4-level demodulation. Any question here? No? Okay. And now this is the thing which is the most important, because this is basically the standard. Direct sequence spread spectrum is the modulation, or it's the technique which is used in almost all of the devices we have we are using now. What is direct sequence? Have you heard about it? No? Yes. Direct sequence is another way of mitigating the security threat, which because of which we had frequency hopping. There might be some eavesdropper who can tune into your frequency. So the idea came that instead of sending your data just by modulating on one carrier, first multiply it with a chip sequence. And chip sequence has much more, has a larger frequency, or let's say has a smaller period time than your data. So this red line is basically showing the chip sequence, and blue line is your data. So you can see that within 1 bit, you have much more bits of your chip sequence. What are the implications? Basically, the rate of your data is increased now. When I multiply it with a higher with the chip sequence with a very small period time. And if we look in the frequency space, what happens if this blue curve shows you the spectrum of your data? This red curve is the spectrum of your data times the chip, right? So we call it spreaded data. Your data is spread in the frequency. And how this thing works, your receiver knows the chip sequence. So your receiver was the intended receiver, right? Not the eavesdroppers. And in the receiving side, they will multiply again your spreaded data with the chip sequence. And if we look at this multiplication, or the bitwise XOR as we say it, if we add 0 plus 0, it's 0. If we add 1 plus 1, it's again 0. So when we XOR this spreaded data with this chip sequence again, what we have is the data. So your chip sequence will be gone from the spreaded data. So in the frequency domain, what will happen on the receiving side, that you receive something which is red, and when you despread it, you will again get the blue curve. Although all the rest of the receivers who doesn't know this chip sequence, they will multiply. Even if they try it out, they won't be able to despread it completely, because for despreading, it's really important that you should know the chip sequence accurately. Okay. Few terms here, which is D BPSK. If we remove D, it's BPSK. BPSK is a modulation scheme which is being, very widely used. What anybody knows about it? What is BPSK? People at the back? Exactly. And what it is? Data is represented in zeros and ones. Amplitude? Yes. Phase shift, right? So phase 2, you have out from the whole 360 or 2 pi phases, one phase is allotted to 0 and another phase for 1. So you have binary, right? BPSK. 2 phases, 1 for 0, 1 for 1. And this D stands for differential. As it turns out that if you change the phase, imagine a sine wave. If you have a sine wave and suddenly the phase is changed, all you have is just, if you are going to the positive side, you will reverse back to the negative side. So this is just one point in time where this phase reversal has happened. So if your demodulation scheme just misses that point in time, there is no way that you can figure out that a phase change has happened. So differential is another way of demodulating it, which is very actually convenient. You don't have to look for that point where phase change is happening, but you just choose one point. If you have the whole sine, you just pick up one point, and after the period pick up another point and multiply them together. If you do all the mathematics, it's very clean actually. It will show you that if both of the sines in 2 periods have the same phase, so you will have like a positive one. But if you have a different phases, it will turn out to be a negative one. So differential is where you don't care when actually the phase has changed, but you take the difference of the two pulses and then figure out if there's a change or not. And QPSK, quadrature phase shifting. What is that? Exactly. So how many bits now I need to use? Huh? 4? 4 bits? 4 phases. 4 phases, how many bits? 2. Right? So I will use combination of 2 bits and use 4 phases to modulate them. And again, differential quadrature phase shifting works for this differential thing. And there is, if you do the mathematics, you will realize there are different numbers you can get from these differences, which will be helpful to tell you what if the phase change has happened or not. So how this thing is worked? Physical medium is using direct sequence spread spectrum, meaning it is multiplying with the chip sequence. And also doing that, it is also using the modulation using binary phase shift keying and quadrature phase shift keying. In the same way, if the signal is good, you can go for higher data rate and use quadrature phase shift keying. If the signal is not that good, you have to use lower data rate with binary phase shift keying. And this is what kind of chip sequence is being used. So if we use 11 chip spreading code, meaning for 1 bit we have, within the time of 1 bit we have 11 chips, and the data rate as we have seen is 11 megabits per second, your effective data rate will be 1 megabits per second. So yes, if we use DSSS, the data is smaller, but there are different ways of spreading the data, and you can use a lower chip rate, or you can basically using a lower chip rate will increase the data which you can send on the medium. Okay, there is something going on in the last row. So please, if you need to talk, either talk it in such a volume that I won't hear. Okay. Third physical layer is something which was in the standard. for completeness sake, but nobody used it. There was no device which used infrared physical layer for .11, but yes, it was there, and there was a proprietary standard, actually proprietary product scheme, which could yield 4 megabits per second for infrared. If we look at the the header format, it's very similar to what we have seen in frequency hopping. We still have synchronization. There is still start frame delimiter. We also have where is that? Yes, signal. Signal is the same as this signaling field we talked about, where the receiver is told now you have to use what modulation. The payload is 1 megabits per second or 2 megabits per second. Service is a field which is just there for future use, but it was not used in .11. And length is just how many data bits to be expected. And header check is the CRC remainder, which is there to check if the header is correctly received or not. That was actually the 3 physical layers we talked in here. PMD. So PMD has 3 versions defined. Now we are moving up to the convergence protocol, which is basically the interface between physical layer and MAC. And what it does basically, if a station is not transmitting or receiving, this convergence protocol layer send a clear channel assessment if the channel is clear or not. So we say it all the time, check the medium, it's busy or not. But physically, how is it done? How the device will know if the receiver, if there is some transmission going on or not. And how it is done is basically either the receiver will know that some synchronization bits are coming, right? If it knows that it has to synchronize on some synchronization preamble, then this is one way of knowing that some transmission is going on. Somebody is using the medium. Another thing is, imagine if you don't have any signal, then you just have noise. So noise should be smaller. The energy the amplitude of the voltage that you are receiving should be smaller. And if you have a signal, the voltage should go up, right? So if the receive energy is more than a certain threshold, and threshold is defined for the noise level. So basically you shouldn't confuse noise as a signal. So if the receive energy is above a threshold, the receiver or the device will know that the medium is busy, somebody is using it. Or if it's below the threshold, it will know that, okay, the medium is free and the device can use it. So in this case, let's assume that the receive energy is below the threshold. Then the physical layer sends this information to the convergence layer that the medium is idle. And this information is passed to the MAC layer. In another instance, clear channel assessment is being done. And in this case, let's suppose that the medium was in fact busy. In this case, what happens, that medium busy information is relayed to the MAC. And then because if the medium is busy, some synchronization preamble is coming, the physical layer will actually get the synchronization information to the upper layers and try to synchronize with whatever is being received. Any question so far? Okay. So now, after the physical modulation, this is the most interesting part of .11 standard, which is basically we have a medium which is open to all, and even in the network there will be multiple stations who are trying to use this medium. How do we schedule them, or how do we, when the stations should access the medium such that there won't be any collisions and the transmissions are received properly. And in .11 standards, 3 versions are defined again, and similarly, as we have seen in modulation scheme, some of the versions are really not used much and have limited applications. And but in the reverse order, we will study this PCF, which is point coordinated. I guess it's framework. F stands for framework. So point coordinated framework is something which is in the standard, but really nobody has used it. The most important thing is DSF, distribute coordination framework, sorry. And it uses what we call CSMA-CA. Collision avoidance, so carrier sense multiple access collision avoidance. What does it actually mean? And instead of going over these words, let's look at the picture. We have 5 stations here, okay? And those downward arrows shows when a station wants to send some transmission. And in the beginning, nobody was transmitting. Station 3 came up, and now station 3 wants to send some transmission. The protocol requires station 3, or actually, in fact, all stations, to wait for a particular time, which is called DIFS, DSF interframe spacing. And it is in the ballpark of microseconds, like 30 microseconds, or 40 or 50 microseconds. Right? So it's really small time. But the stations want to wait, should wait, because it might happen that some other stations are transmitting at just a temporary phase where nobody is sending some data. So the station should make sure that medium is actually free. So if, in this case, the station 3 listens to the medium for DIFS, nobody transmits anything, medium was idle. After DIFS passed, the station 3 started transmitting its data. But in the meantime, station 1 and station 2 and station 5 also wanted to send some data. But when they have waited their DIFS, they have sensed that the medium was busy. In case of station 2 and station 5, the first time they sensed the medium was busy. So what they did, they waited for the transmission to end. And when the transmission has ended, because one station doesn't know that there are other stations who are also waiting, right? So if all of them start sending when the medium is idle, then there could be some collisions. So what they do, they wait for another DIFS, another interframe spacing, 40 microseconds, and then they start a random backoff. And random backoff is between a specific time. So they have, from 0 to 2 seconds, I have to choose a random time, and then I have to wait for that. Why this random time is used? Just to avoid the collisions. Because if I have a random time, it's really unlikely that both of the stations pick up the same random time. So in this case, what happens? That station 2 has chosen the least amount of backoff timer, and their time has finished, and then they sense the channel again. Nobody is sending anything. Station 2 has started sending its transmissions. At the same time, station 1 and station 5 knew that now somebody else is using the medium, so we cannot use it. This green bar shows that they freeze their timers at that point, right? And then they start waiting for the medium to become idle. Freezing is actually helpful. If they don't freeze and just start the whole process again, what will happen that if I am waiting for the medium and my backoff timer was larger, I won't get any priority. But if I freeze my timer in the next cycle, there is chance that my freeze timer will be, in general, smaller than the stations who are picking up the backoff timer from this random window, right? So this freezing actually is done to give priority to those stations who are already waiting. In this case, now we are here, Station 2 has stopped sending its transmission. All the stations are required to sense the medium again. Station 1 again started its back-off timer from using the remainder value, and station 5 also started using the back-off timer using the remainder value, although station 4, which has come while the transmission was going on, has to choose a new back-off timer. And in this case, it might happen, there is a very small chance that both the two stations or multiple stations may choose a same back-off timer, and they have to start, they start sending the transmissions at the same time. It might happen. There is a non-zero probability of such thing happening. In that case, what will happen? The receiver won't send acknowledgements. And when the receiver won't send acknowledgements, the sender will resend the transmissions. So this back-off timer scheme or collision avoidance scheme just lower that probability of collision, but does not eliminate it. Okay. So basically, how it does, how it works: sender sends the data, and receiver sends an acknowledgement. That completes the whole transmission. And if the acknowledgement is not received, the receiver will send the data again. We had another option here, DSF with RTS CTS. Let's see what it is. And actually it comes because here we have a problem, hidden terminal problem. What it is basically, A wants to send some data to B, C also wants to send some data to B. In C sensing range, A is, A doesn't know about the sensing range of C, C doesn't know about the sensing range of A, right? They both sense the medium, they both find that, okay, medium is idle, and they both start sending the messages at the same time. However, B cannot receive multiple transmissions. If they have, if they are using different channels, it's a different thing. But in general case, the transmission will be collided at B, and no successful transmission can happen. This is called hidden terminal problem because C is hidden from A and A is hidden from C. In order to counter that, there is the option of having RTS and CTS, request to send and clear to send. For example, let's suppose that A wants to send some data to B, and A, instead of sending the data, when it checks that the medium is clear, it sent a request to send message. And this request to send message will be heard by all the devices which are in the neighborhood of A. Of course, C doesn't hear it. But if B also finds that the medium is clear and it doesn't have any pending transmissions or receptions, B will send a clear to send message, CTS. And this transmission which B sends to A will be heard by C. So C will know, okay, somebody, although I cannot hear the sender, but somebody is sending the transmission to a node where I also want to send some messages. So the CTS will be heard by C, and then C will also stop sending messages to B. Just, this RTS CTS is a thing just to avoid the hidden terminals and let a larger group of devices know that a transmission is going on in this neighborhood. And these RTS CTS messages also have this nav vector, network allocation vector. It basically tells you the duration for which the sender wants the medium to be idle. So all the devices in the neighborhood listens to this nav value, and while the nav value is active, they won't send anything. So it just tells you, okay, this is the time for which you need not to send anything. And interestingly here, nav of RTS and CTS are different, because RTS nav also contains the time the system needs for sending CTS. CTS message, in this case, A will send RTS to B, and RTS will have the whole duration, including the time B will take to send CTS back to A. So it is clear in here. RTS is sent from the sender, CTS sent is from the receiver, and when it's all clear, data is sent, and when acknowledgement is also sent back from the receiver. And all the other stations will look at this nav field to stop all the communications. Okay, let me see. Yeah, let's any questions so far? Anything not clear? I missed one term we used in this figure, SIFS. I didn't explain what it is. It's called short interframe spacing, and it is short because it's even smaller than DIFS. So if DIFS is in the ballpark of 50 microseconds, SIFS will be 20 microseconds or 25 microseconds, something like that. The whole idea is that when the receivers or the transmitters are sensing the medium, they should wait for a while. So maybe it's a temporary idle period, and the transmitter will start sending the messages again. Just to avoid that, it's better to wait for a few microseconds and to make sure that actually the medium is idle. Anything not clear here? No? Or everything is not clear?
SIFS and DIFS is basically the idle period.
In the idle period, when the transmitters just have to listen. Yes. Yes. Any other question? No? Okay. Another interesting thing is, actually it will deviate from what we are studying here, but new researchers which are actually trying to calibrate the performance of RTS, CTS or .11 without RTS and CTS, they have concluded that RTS, CTS, although they are there to avoid collisions, and if you avoid collisions, basically maximize your throughput, but RTS, CTS are not that good because it inhibits a larger number of devices. And maybe it's not really necessary that all of the devices should stop their communication while a pair is communicating, right? Because what happens that this carrier sensing is very sensitive. So even if this RTS CTS thing, which are very small messages, and we will see that they are just 20 bytes or 25 bytes messages, they can reach longer distances. Although your actual data, which is usually 1000 byte frame, reaches a smaller distance. So basically, if your RTS CTS reaches a larger distance, you will inhibit a lot of devices in that larger neighborhood to stop communications. Although when you actually start your communications for the actual data, it won't actually disturb those nodes which are on the periphery of your neighborhood. So there are just some issues with RTS CTS. It solves one problem, but again there are certain issues. Another way of avoiding collision is doing fragmentation. Don't send larger data frames. But what do you think? Why fragmentation could help? Just because if you are sending smaller packets will be in the medium for a smaller time. So if you see it probabilistically, if you are using the medium for a shorter time, there is lesser chance that another station will start using the medium. So if you don't want to use RTS CTS, break your packet into smaller packets. Another thing interesting is, if you do all those checksum calculations later, and you realize, okay, checksum is not, it's indicating that there is some error in the frame. What you do, you ask for resend. So if the packet is larger, the transmitter needs to resend the whole big frame. But if the packet is smaller, you can do this check for each smaller packet, and you don't have to resend the whole thing. So fragmentation is another solution to combat this collision thing, and we will have an example actually later where we actually do some calculations and see what will happen if we do some kind of smaller packet, compare smaller packets and larger packets. Even in the devices, if the packets are larger than 1,000 bytes, then devices use RTS-CTS. Otherwise, they just use CSMA-CA without RTS-CTS. And this is the last thing, point coordinated function. Basically, it requires that you have a coordinator. So if you have an access point and multiple stations are connected to that access point, it's much easier. So instead of each station accessing the medium, sensing for the medium to be idle, and then sending its messages, coordinator can schedule the transmissions, and coordinator can tell, okay, now it's your turn. Now station 1 will send its transmissions, and then station 2, and then station 3. So in infrastructure networks, it's a much more easier thing. It has higher throughput than CSMA-CA because for carrier sensing, time is wasted. If you have a proper coordination going on, it's much more easier. It's much more efficient. The downside is it requires coordination. In distributed coordination function, one station come up, no scheduling is needed. It can just sense the medium and start using it when the medium is idle. So distribution has the cost of wasting some time. Here we have PIFS, another interframe spacing terminology. P stands for PCF. So PCF, interframe spacing. PIFS and DIFS are quite similar to each other. So this figure says that when the point coordinator is polling each station to send its data, the other stations are notified by this nav vector, network allocation vector, that you shouldn't send any transmission while this coordination is going on. MAC frame, we have talked about the 5 frame so far. MAC frame should also have the way of telling who sent it, source and destination information. So these 4 address fields, address 1, address 3, address 4, they, in some combinations, they inform the destination about the sender information. They also contain destination address sometimes. If the transmission is between a station and an access point, it has this basic service set ID. So, using these 2 bits here, to DS and from DS, I actually have a figure here. So using these 2 bits, there are different information that we can put on these address fields. And basically, just in simple terms, it has the information about the sending party and the receiving party. Other things are sequence numbers. So because we know that some packets may be lost and some packets may be resent, how do the receiver know that's a resent packet? Sequence number basically tells the receiver that, have you seen the sequence number before or not? And we also have, again, CRC. CRC is just for the header. The receiver will use this CRC to check if the header is error-free or not. Duration ID is, duration of the data transmission should be known to other stations so that they can stop sending the transmissions in the while. Protocol version is, again, 11B or what kind of protocol we are using. It's what kind of modulation type. Sorry, it's not the modulation type, it's MAC. So it's RTS, CTS, it's simple, CSMA, CA, what kind of protocol is being used. And retry Retry has the information about, is it a recent packet or it's a new packet. If we have used fragmentation, this bit is set, which actually tells the receiver that it's the fragment number 2. More fragments are coming. And interestingly, we also have another thing, WEP. WEP is Wired Equivalent Protocol, or it's also called Wireless Encryption Protocol. And here we are talking about .11, which is the initial standard. So if we think about those devices we had 2-3 years ago, they all had WEP in there. But WEP was set as an option. So WEP was not set as a default. So users can set this option if they want, or they can use their devices openly without using any encryption mode. Now the things are reversed. Now we have a better encryption protocol, and it's set as default. So users can deselect it. They can, say that they don't want encryption. But if you just use your device, plug it in, push it on, it will have encryption automatically in there. WEP was an encryption standard. It basically what it does. It takes a key and it takes an initialization vector and use an encryption mechanism to generate another data stream. And the way this key and this encryption scheme is selected, which has actually multiple mathematical operations, that it will be difficult for people who are listening to your communication to realize actually what has been sent. And it will be difficult for them to decrypt what has been sent. But in the modern world, there are many intelligent hackers. And what they do, instead of looking at just one message, they listen to the bit stream for a while. And it turns out then that if you have packet by packet encrypted using WEP, the initial bits are quite the same. And if you just look at the initial bits, you can figure out what is the key. So when WEP security is gone, the thing was that we need some stronger mechanism, and the stronger mechanism, which is called WPA, which is now every device has WPA, it's the same structure as WEP, only the key is longer. Actually, not the key. The initialization, the vector, the seed you use, the seed is longer, and the key is changed after a while. So there is a mechanism where the key you use for encrypting the data is changed after a few seconds. So, even if there is some intelligent hacker and he compiles all the transmissions, when the key will be changed, the initial bits will be changed. So it will be difficult for him to realize what is the key the transmitter is using currently. And it's very, we really sometimes take these things for granted. But in NICTA, we did some experiments near University of Sydney, and we had 8.11 nodes on streets, Cleveland Street, Broadway, Abercrombie, and I think it was the 4th day when the network was up. We had the first break-in. Somebody really tried to log into the network and tried to break into the network. So it's it's quite normal. It happens all the time. Power management. Yes, I left it. Power management is an option. So if there are PDAs or mobile devices, power management schemes are used. Otherwise, they are not. So power management, we'll see what they are. They are adding extra complexity on top of what we have. I think I have everything here. Types and subtypes, because your frames could be used for control messages, your frames could be used for data. So these type and subtypes basically tells the receiver this frame is about what. I talked about that. And yes, here, see these are the very small messages we use for RTS CTS. 16 bytes. And what they have is basically telling the the control frame, which tells what kind of frame it is. It's RTS, it's CTS, it's acknowledgement. Duration contains the duration which we use in NAV, network allocation vector, so that the neighborhood will know how much time the transmission will take. And receiver address, and again this whole thing needs some error check. Okay. So that concludes the medium access schemes. But the question is, CSMA-CA is not the only one we study in fundamentals of telecommunications. There are other medium access schemes. So if you have multiple devices trying to use the same medium, you can use CSMA-CD. CD stands for collision detection. So Ethernet works on CSMA-CD. Every device can use the wires. If two devices or multiple devices use the wire at the same time, there will be a collision. That collision could be detected by the devices, and then they can back off and resend the messages. Why not we do the same thing in wireless? Why not? Why not we used CSMA-CD?
Hidden terminals.
There are hidden terminals, yes, exactly. It will be, yes? Exactly. You might not detect the collision. Collision might happen and you might not detect it because the energy levels of transmission and reception are very far from each other. Transmission levels are much higher, and they can actually, make the receiver blind towards detecting the collisions. So collision means that you actually have to detect a larger, an even larger power level, but you cannot detect it. So it's difficult to detect collision, to detect collisions. Okay, what about FDMA? FDMA, what does it say? You have one frequency carrier for one device, one channel. Typical GSM style, not GSM, cellular style, basically. What do you think? Why not? There is limited spectrum, but another thing, if we go back, FHSS is kind of FDMA, right? We have those subcarriers, we allocate those subcarriers to devices, but we were not allocating them statically. We were hopping, and when we were discussing that, we said that hopping is better from security point of view. Hopping is also better in terms of frequency selective fading. So if one carrier is bad because of frequency selective fading, it will be better to use hopping instead of a static allocation. And TDMA. Actually, I actually this FDMA and TDMA is why not is not the right question, because this point coordination function is kind of TDMA, right? Where the point coordinator or the access point is allocating time to different stations. So it's kind of TDMA. Time is divided between the channels, between the devices. But the downside is coordination is not free of cost. So if we have ad hoc mode, or if we have multiple devices coming together in a distributed fashion, point coordination could not be used. So it's very important. FDMA, TDMA in this typical sense, you allocate resources to one device, requires that there is some entity which has the authority of allocating those resources. So if you are working in a distributed fashion, you cannot have this kind of medium access where coordination is required. Okay, so carrier sense multiple access is the most favorite in 4.11 just because it's distributed. We also had in those layers we were looking at, we had physical layer and MAC layer, and we also had management layer. And I also said over there that management layers take care of the main purpose is association, reassociation. When you come into near an access point, you need to negotiate, and it checks if you have the authority to use the network or not. So this authority may be in different ways, and there are different ways you can set your devices. Even the normal devices you can buy off the shelf. You can deselect your encryption option. You don't want to use encryption option, or it's set by default. Or you can also specify MAC addresses. So if you are not using encryption, because people don't want to use encryption because it slows down the speed. So if you don't want to use encryption, you have the choice using your normal devices that you can specify MAC addresses which could use this access point. So even if you're using this device at home, and other neighbors can also look at your access point, it's open, it doesn't look as locked, but they cannot still use it because their MAC address is not recognized by your device. So there are different ways you can set it up. Power management is there only for battery powered devices. You will see what it is, and different synchronization functions and different management functions. Synchronization is basically, even if the devices are synchronized, there is clock drift, and they might be unsynchronized after a while. Dot 11 defines this beacon strategy. Access point is required to send beacons after a specific period, and all the stations need to time synchronize using that beacon. The interesting thing here is the beacon can only be sent if the medium is idle. So even if the access point wants to send it at, let's suppose, 2:45, it cannot be sent at 2:45. It might be sent after, let's suppose, half a second later, just because the medium was not free. To combat that, beacons use timestamps. So the stations also look at the timestamp of the beacon and then try to synchronize it. But again, there is an error. So this synchronization is not very accurate. But this is the best the system can have. Yes?
What exactly is a beacon?
Beacon is a small message, just maybe 2-3 bytes.
Okay.
Yes. With just the information that it's a beacon, the stations need to synchronize using that message. And things are even more complex if there is no access point and devices are working in ad hoc mode. So it might happen that both of the devices send the beacon at the same time, and both of the beacons collide, and none of the beacons are received. So in ad hoc mode, stations are required to add a random delay. Random delay is just to avoid collisions, and beacons need to be time-stamped. Power management is basically yes, any question? In all the systems where battery-powered devices are used, power management has a simple philosophy. Just turn off the devices when they are not in use to save power. The interesting thing, actually the challenge is if they are sleeping, when they will know that there is data that they need to receive. If they have to transmit some data, that's fine, they know it, and they will wake up and transmit the data. But how they will know that there is data for them to receive? To combat that, there is this terminology, I won't go into that, just how it works. Stations are required to wake up periodically. So they wake up after, let's say, 1 minute, checks the medium, checks that if the access point has some message to send, and if there is some data to be sent to the station, access point is required to send a small message which could be received within the waking cycle. So this small message is just an indication. You don't have to sleep, there is data for you. So this T This D here actually stands for if access point needs to broadcast something. Broadcast meaning that most of the most of the stations need to wake up because there is a broadcast meant for multiple stations. So the station needs to wake up till the broadcast happens. A T stands for a unicast message. Access point has message for a specific station. Only that station needs to wake up. All of the other stations can go to sleep. So in that case, in the second time slot, only the station we have here didn't have any data to receive, so it went back to sleep. But in the third slot, it also had some data to receive, so it waked up for a longer period of time, received the data, and then went to sleep. And again, in ad hoc mode, it's even more complex because now the data could collide with each other. So for all those indication messages, the stations need to add a random delay. And that random delay is, with the hope that not two stations have the same amount of random delay. Okay, we say that .11 supports mobility or roaming, but the way it is supported, it's not in the strict sense of supporting mobile devices. .11 was meant for those devices like laptop, which will be sitting on a desk and then people are using it. If you use a PDA and you are walking, and say your associated access point has a bad signal strength, you need to associate to another one. The way it works, all of the sessions that you have to your application, it just terminated. So your data, if you're accessing a web page, you won't access it until you have those MAC management issues resolved. So you got dissociated from the access point you are connected with, you get reassociated to another access point, then you need to send the request to the web page again, and then you get the data. So in .11, it's not that you can have mobility and it's seamless. It's not there in the protocol yet because it's not meant for really highly mobile devices. Okay. Any question so far? I hope I didn't lose you. So 11B summary. 11B has different data rates supported, 1 megabit, 2 megabits, 11 megabits, using different kinds of, most of them are using DSSS, spread spectrum, direct sequence spread spectrum, and different data rates depend on what modulation you are using and what kind of spreading chip you are using. Range, we also had in our initial chart. Frequency band is 2.4 gigahertz. 11B had WEP, which is insecure, but now the modified standards has a better encryption mechanism. It also has this SSID, which is your service set ID. So, service set ID also act as a security feature. So foreign devices can access your access point. There is option of defining the one ID for a specific basic service set. Okay. And another thing which is there we have seen those packet formats already. We have seen this one before. There is another option for a short data unit format, which has basically the short thing is just using half of the synchronization bits instead of the full 128 synchronization bits, and actually it's less than half. So this basically, if synchronization is not a big problem, especially if you have good signals and good links. So you can basically cut down over there and use a shorter pulse. Sorry, shorter sequence. Another thing which actually we talked about in the beginning, that see here, payload can have different data rates, but your header is always 1 megabits per second using binary phase shift keying for spread spectrum physical layer. And here in the short data unit, your initial where you have this detectors are always 1 megabits per second, and data rates are increased. They are, the rest of the header is always QPSK. So, you cannot use multiple modulations. There should be a specific one. Doing that, if we look here the header was taking 192 microseconds, although here it's smaller, it can only take 96 microseconds. But again, we are using QPSK. It directly implies that your signal strength is better. So if your wireless links are better, you can use a short header. If your wireless links are not that good, not strong, you have to use a long data unit. This PPDU basically says physical protocol, I guess, data unit. Okay. And these are the spectrum, how it is allocated. 2.4 frequency space for .11 technology is divided into 11 channels, and these 11 channels are not non-overlapping. So although there are 11 different choices, once you have your device, actually the default is 6. So if you don't change it, your device will always use channel 6. But if you want, there is option, you can tune your device to different channels, and there are 11 choices. But those 11 choices are not non-overlapping. So even it doesn't mean that in a neighborhood 11 devices can work without interfering into each other. No, these if you look here, after channel 1, channel 7, and channel 3. Actually, it's Europe. So Europe divides the whole spectrum into 13 channels. US divides the whole channel into 11. In Australia, we also have this 11 channel format. So channel 1, channel 6, and channel 11 are non-overlapping from each other. If you look at 2, 3, 4, they will be, 2 will be slightly shifted from 1 and 3 will be slightly shifted from 2, but they will be overlapping to each other. 11A is, instead of 2.4, it uses 5.8 gigahertz, and I will only emphasize on the important points as we are running out of time. Here, see, one channel is 22 megahertz long. In 11A has much more channels defined within the frequency that is allocated for .11, but each band is 16.6 megahertz wide. But if we look at the data rate supported by 11A, it can go up to 54 megabits per second, whereas in 11B we only had, the maximum was 11 megabits per second. So frequency band is related to data rate. If you have larger frequency band, you can send more data, but it's not really a linear relationship. It depends on what modulation you are using, how you have defined your physical layer. So see here, instead of 22 megahertz, we have now 16.6 megahertz, but still we have higher data rates, and the reason behind that is that spectrum is used much more efficiently than 11B, and it's because of this OFDM technology. And OFDM technology, what it does, basically it divides the 16.6 megahertz into smaller subbands, and these smaller subbands are overlapping to each other. But if I think I have another Yes, here. If we look here, these are different, different devices. Assume that there are different nodes trying to access it. These different devices, these different messages are first they are shaped by a pulse shaping filter. Instead of rectangular pulse, you have a Gaussian pulse. It is modulated over a carrier. So modulation basically means we use a frequency, and then the carrier basically defines what frequency the message will be used. So here we have, I'm not sure if it is clear to you. Here, let's suppose it's W1, W2, W3 up to Wn-1. In the end, all those messages are summed, and this is HT is the combined message which is going on the medium. And let me do some calculations here and see if I achieve that. So basically we have So basically we have E minus J omega I t, and I am multiplying my message with it, xi, and I am summing it over all I. This is what in the next slide we refer as ht. And sorry for changing the symbol here. This is same, let me call it AI, just to be consistent. Okay, so AI is one message, and there are multiple users which are accessing it. We use different WIs for each of them. Now what happens on the receiving side? I will use this HT and multiply it with a specific carrier, which is, let's suppose, E J W 1 T. By doing that, what will happen if I just use the sum? I will have I A I E J omega 1 minus omega IT. Okay. If I equals to 1, what will happen? This term will become 0. Omega 1 minus omega I will become 0. And e raised to power 0 is 1. And I will have just the component A1, right? So if I equals to 1, this sum will give us AI. And if I is not equal to 1, if I is not equal to 1, sorry, what is happening? Sorry. Eraser. If I is not equal to 1, I not equal to I is not equal to 1, okay? This will be a combination of cosine and sines with the frequency of W1 minus Wi, right? And if we have cosine or sine with a certain frequency and we integrate over the whole period, what will happen? Sine has a positive area, sine and cosine both have a positive area and a negative area, and both are the same, equal with opposite signs. So if I integrate the whole thing, meaning I have the sine and I integrate the whole thing over a period, it will be 0. So if I integrate the whole thing, over the period, and period you can find out from WIs, right? The whole thing will be 0 if I is not equal to 1, right? Something I missed here. What I have missed, that all those WIs are basically multiple of some specific frequency, F naught. If there are multiple of frequencies, that means that their periods are also multiple of each other, right? F naught is 1 over T naught. I'm sorry, I should be precise. There should be a factor of 2 pi. So Wi is defined as 2 pi times I over F naught, and F naught is this fundamental frequency, the fundamental frequency concept we use in Fourier series. The thing is, if we use those carriers which are multiple of some specific frequency, which is our fundamental frequency, at the demodulation side or the receiving side, we can just take the message which is modulated on the specific carrier just by multiplying this specific, like if we want to have the first component, we can multiply the jumbled up signal with the first carrier and get only the first message out. All of the rest of the things will become 0, right? This is the same concept we actually use in modulation. You have a cosine, you multiply it with the carrier, and then you filter it. Filtering and integration is mathematics of low pass filter. So you filter, you take your message out. Okay, same concept is happening here. The nice thing is doing that, using those orthogonal frequency components, frequency carriers, which are multiple to each other, multiple of a fundamental frequency, we can pack so many subcarriers within our frequency band. In 16.6 megahertz, we can have up to 52 subcarriers. 4 are used for control, pilot carriers, and 48 subcarriers can use for data. And then let's imagine, we have those subcarriers. These are the frequencies which I'm using. If I use different phase shift keying on top of it, like QPSK, right? So I will have 4 phases. 4 phases, 1 subcarrier, meaning I can use 2 bits and I can map 2 bits on 1 subcarrier. If I go for an amplitude modulation kind of scheme like 16 QAM, actually I have a slide here. So if I use a higher order modulation like 16 QAM, what it does, it defines 16 levels in the amplitude. And how many bits I need to have 16 levels? 4. So I can use combination of 4. And each combination will map into 1 modulation. And this all is being done using 1 subcarrier. So I had 48 subcarriers, and each one can carry 4 bits. If I go to a higher order modulation, 64, each subcarrier can carry 8 bits. So if we look here, and we didn't talk about coding so far, but I think we should do this exercise as our tutorial question. That would be nice. If we do that, we will see when we will complete this whole chart that data bits in the end it should become 50, 54 or 58 what we had over there, the largest one. Yes, 54 megabits per second. So 54 megabits per second actually use 64 QAM modulation over this OFDM layer. And this OFDM is so robust. It's becoming so much popular. Now WiMAX has OFDM physical layer. The cellular system is going towards using OFDM. The long-term evolution, as we say, for cellular networks, LTE, basically will use OFDM in future. Right now 3G doesn't have OFDM, but it will use OFDM. Just because it has tremendous capacity. And let's complete this chart. So we didn't talk about coding. Coding is done to mitigate errors in the channel. So a simple trivial example. If there is channel probability that 50% probability that my reception will be successful, it is I send something, it might happen that with 50% chance that it will become erroneous, right? But if I send the messages twice, what will happen? The error chances will become smaller, because now both of my transmissions should be erroneous, so that the whole transmission will fail. If I do redundant transmissions, if I repeat my transmissions, there is chance that my reception will be successful. So, same.
But, if I transmit twice, it means that I increase the chance of the collision, isn't it?
If I am the sender, I won't send it at the same time, right? I will send it one after each other. But that concept was in when we are looking at the messages. But if we look at bits, coding rate half means what? It means that for every bit that I need to send, I will send, instead of 1, 2 bits. Okay. So, trivial example, nobody uses that code, that if you have to send 1 bit, send it twice. But nobody uses it because it's meaningless. But half rate code could be that you have 4-bit block, and for 4-bit you added different parities. That if it's even parity, if you just say that, okay, if my block has even number of ones, my parity bit will be 1. So some kind of checks, if you add into it, the receiver will look at those checks, tally it, and if everything is fine, it means your data block is fine. So different kind of coding schemes are being used with different coding rates. Half means for every 1 data bit we are sending 2. So if our data rate is 6 megabits per second, our raw bit rate will be how much? How many bits we need to send on the physical channel to achieve 6 megabits per second? 12, exactly. And similar thing for 9 megabits per second. If you use 3/4 coding rate, that means for every 3 bits we have to send 4. The raw bit rate will be 12. Yes. So we can check. For 12 it needs to be 24, and so on. Now we are using different modulations. So we have combinations of different coding rates, and we have combination of different modulation. Modulation BPSK means that I will have 1 bit mapped into 1 subcarrier, right? 0 will go to 1 phase and 1 will go to another phase. That means 1 bit. 2 phases, 1 bit. So how many? It means, I think, yes. Okay, I have it here. So 1 bit per subcarrier. 1 subcarrier will carry only 1 bit. BPSK again. How much? What about QPSK? 2, exactly. How about 16 QAM? 4 and 64? 8. 6, sorry. Yes, 2 raised to power 6 is 64. Okay. Next thing is coded bit per OFDM symbol. What it is? It means that in one OFDM symbol, we have altogether 52 subcarriers, and out of 52, 4 were used for pilot, so we had 48 dedicated for data. So if here we were looking at per subcarrier, if we go to per symbol, how many bits we have in one symbol of OFDM? In the first case, 1 bit per subcarrier, we have 48 subcarriers. How many bits? 48, yes. Simple answer is right. How about QPSK? Double it, right? Yes. Ouch. Okay. And the last column says the data bits per symbol. And the thing which we have to consider here is, up till now we have coded bits. So coding, we were talking about raw data, how many additional bits we need to use for coding. But now we are talking about how much we are, what is the throughput? What is the data bits? What is the data content within one symbol? So for first case, what will be the data content within one symbol of OFDM? Exactly. Second one. Now? It's 3 by 4. 48. 36. 36. Divided by 4 times 3. Yes, 12 times 3, 36. And if we, the information we have at the bottom, fixed OFDM symbol rate is 250,000 symbols per second. If we use that and multiply our data bits per symbol, we will again get the first column back.
How did you get the 48?
48, which one? This one? This column?
Yeah.
We have 48. Oh, it will be difficult to go back. But we have 48 subcarriers in one symbol. And one subcarrier has 1 bit. So altogether we have 48. So 54 megabits per second, the highest data rate is achieved if we use 3 by 4 coding rate, which is which is much efficient than using half. And we use 64 QAM, then we can achieve 54 megabits per second. And it means that 54 megabits per second can only be delivered if wireless links are really good. But if they are not good, then we have to go back to 6 megabits per second. Okay, and the way it works, we have variable data rates here, and the information is reserved in signal, which says what kind of payload is coming. Okay, and then we have many alphabets there. I will just talk about few of them. 11G, because if 11A, 5.8 gigahertz use OFDM, why not 2.4 also use OFDM? There is nothing which stops you. So another standard 11G is same as 11B, meaning 2.4 gigahertz frequency spectrum is used with OFDM layer. So in 11G, data rates are, they are up to 54 megabits per second. Just because instead of direct sequence spread spectrum, OFDM physical layer is used. Right now, if you buy a device of a wireless router now, most probably you will have 11N. And 11G is there, I think, for the last year. All the devices we have is 11G. But 11N is a new one, and data rates are even going up to the 100 megabits per second range. And how they have achieved this data rates, that instead of using one antenna for one signal, they use multiple antennas. So MIMO is a technology, multiple input, multiple output, and basically what it does, sometimes signal you receive at one point could be bad, but if you just move half of a wavelength away from that point, signal might be good. So if you have two antennas and you combine both of the results together, your reception quality enhanced. So MIMO uses this concept of using multiple antennas, or space diversity is also the term used for it. And just because you have good signal, just because you have a stronger wireless link now, you can use higher data rates. So even higher than what we have talked about, even going up to a lower coding rate and using a higher modulation. Interesting things. Yeah, 11P is also an emerging standard. 11P is where your cars will be automated, and they will be talking to street side routers and sending information there and getting information from there. And the most talked about application for 11P, which is the vehicular standard, is that it will have a early warning system for collisions. So if driver response is, let's suppose, 5 seconds before applying the brakes, this wireless system will give the automated control even lesser time to apply the brakes. So some collisions, some accidents could be avoided. But it's a whole system. It's not just wireless links. It has sensors. How do you sense the medium? You don't want to apply brakes unnecessarily. So, all those issues are there, and people are working on it. Okay, just briefly, I won't go into the details of Hyperland. We talked about that Hyperland is a European counterpart of a .11. It's an interesting story. Hyperland has better technology than .11, but manufacturers didn't like it. It's not because of that it's not technologically strong, but it's just that it has so many features and manufacturers thought that people don't need them. Hyperland, in .11 people are now talking about providing different quality of service, like you have VoIP calls providing different quality of service to it, video, different quality of service. Hyperland had the quality of service from the beginning. But people didn't think that it's that important to have a complex system. A2.11 is much more simpler than Hyperland, and Hyperland actually it has the different applications. It's not just wireless LAN. When we talk about wireless LAN, it's just wireless LAN means Hyperland 1, Hyperland 2, and Hyperland 3. They are WiMAX equivalent of what we have in the 802 IEEE 802 standard family. And just to give you an idea, this distributed coordination function we talked about in 802.11, this is the Hyperland equivalent of that figure we talked about with back-off timer. That was even complex for us. And look here how many different stages Hyperland defined to solve the contention. And priorities means that they define priorities to different devices and priorities to different applications. So first they resolve who has the priority. And if there are multiple senders with the same priority, there is another phase which basically decides which one to send, because they have the same priority. So it's, I'm not going into the detail because it will take a lot of time, but they are there in the notes if you want to read about it. No products, but interestingly, some of the mechanisms are now emerging into .11 standards. And I guess let's do this example. That would be, I have another example, but I will give you the solutions as well. You can look over it. But let's do this problem here. Read it. Here in this problem, we will see the difference of longer frames versus smaller frames. So it involves some of the statistics, but let's look over it and see if we can do something, and then we will solve it together. Ballpoint pen. Okay. So what I'm saying is, let's assume that LS is transmitting something here. In this case, and both of them are the same, so it doesn't matter, we can choose either one. In this case, if Bob transmit a packet, probability, P stands for probability that n is anything greater than 0. This probability will be probability of collision. I realize if I don't break, it's better. Is this point is clear or not? And we can find out this probability because we have the distribution. This distribution, if I add all the probabilities for n greater than 0, meaning this will be equal to, I will sum over n from 1 to infinity of this expression, which is e minus lambda t lambda t n over n factorial. Is it clear or not? This is, we have the probability expression given for a specific n, and we say that if this n is anything above 0, that means there will be a collision. So probability of collision is basically summing all the probabilities from 1 to infinity. And when we have something like that, it's much more easier to write it as 1 minus probability that n equals to 0, right? Because Poisson can only take values of n from 0, 1 to infinity. So if n equals to 0, we will have minus lambda t, and this is it. 0 factorial is 1, lambda t raised to power 0 is 1. So this is the value. And look here, if now this expression depends on what is lambda and what is t. So if lambda is larger, that means the average the average number of sent packets are larger. Alice and Bob are sending more packets, then this probability will be larger, right? Because we have two minuses here. And t, how do we calculate t? Now for calculating t, we are given 1 megabit second data rate for the channel, and we know how large is the packet. Can we find the time the packet will take over the channel? If we know the line rate, the channel rate, and how we will find it out? T for 64 byte packet will be how much? What should I do? What should I do? Divide what by what? Number of bits by the line rate. Exactly. So 64 bytes means 60, because my bit rate is in terms of bits, so I will multiply it by 8 and divide it by 1 mega. It will give me some number. What is that? Microseconds. Okay. How about the second one? This is for 64 bytes. How about for 1000 bytes? 8 milliseconds. Okay. See, the time has increased significantly. So if time is larger in this expression for the same lambda, our probability will also increase. And I have here, let me go back. Okay. Okay. And show. I have a graph here which shows okay, it's here. So blue curve is for 64 bytes and green curve is for 1000 bytes. X-axis we have lambda and y-axis we have collision probability. So you can see if lambda increases, meaning the average number of packets transmitted in 1 second, average number of packets increases, the probability that there will be a collision increases very rapidly for 1,000 bytes. But it increases for 64 bytes, but the increase is not as rapid as 1,000. Okay, so smaller packets have smaller probability of collision. So fragmentation makes sense if we see this kind of mathematical formulations. Okay, any question? Yes?
What's the equation of that graph?
Equation is the same thing. 1 minus e raised to power. Yeah, it's here. This one. It's here. Okay. Now it's up to you. If you have energy to go over the second problem, I have second problem. If you want to take it home, here are the solutions. I will leave both for you. So it's up to you. I'm happy to go over the second problem as well. Want to do it? Okay. Any questions so far? Anything not clear? Okay. Okay, I think I did something wrong here.